So, well, let's dive into the presentation right away. We don't have much time, and there is enough material to cover. Am I audible at the end? Okay. So, why do we want to this? Why do we want the shared buffers to be resizable without requiring restart? I mean, anybody here who doesn't want that facility in PostgreSQL? Okay. So first reason, and probably main reason, is high availability. Nobody likes to restart a server. When it's running, it's happy, nobody wants to disturb it, because we don't know what will happen if we shut it down, whether it will come up next or not. So high availability is an important criteria. But in today's day, with the elastic clusters in there, where we have elastic computes, we can add more compute facility, we can add more number of computes, and with that, the working set or the amount of the data that gets operated upon at a given point in time, that changes. If we have multiple computes, probably each of those computes is serving a different application, different data set. If one of them goes down, the other computes take the responsibility of the compute that has gone down. Then these other computes have their working set changed. So while all this is happening, if the buffer pool does not keep up with the working set, we have a problem. We have elasticity, but then after the cluster is restructured, it is not able to take the load that it used to take before. For that, if we require to restart each of those compute, then that defeats the whole purpose of having multiple computes there and separating compute and storage. So with the new architectures of serverless elastic computes, this problem has become even more serious. The third motivation is optimal memory usage. We often do not know when we first start our database server, we first deploy our application, we do not know how much buffer size is optimal. And so usually people either size it pessimistically to be very less, or optimistically to be too high. And I mean, we never get to a point where we have optimal number of buffers. And so we either pay in price or we pay in terms of high availability, because then in order to change it, we have to restart. Another class of tools, there was a talk of PGTune last year, which is basically a tool which uses genetic algorithms or AI methods to tune the parameters for a given working set, given application. And what that does is it tries one set of parameters, sees the performance, next set of parameters sees the performance, and that's how they come to an optimal set of parameters. Shared buffers is one of the parameters which affects the performance most. And so most of these tools, they have to resort to restarting a server when they change the set of parameters. Again, increasing the amount of time that these tools take to come to an optimal set of parameters. Yeah, the problem is not simple. We cannot resize buffer pools just like that. It's almost like an open heart surgery, and we'll see why. But before that, I would like to talk a bit about shared memory. There was a talk earlier yesterday about shared memory, so I'm going to sort of build on top of it, but maybe in more gory details. So what happens when you first start the server? There is only postmaster. And as you know, a process has these segments in memory. There is data segment, there is code segment, heap, stack. Similarly, postmaster creates a shared memory segment to which it requests OS to give memory in such a manner that that memory is shared by other processes as well. There are different ways to do that on different operating systems, but essentially it comes to this point, and that becomes the shared memory segment in the address space of Postmaster. So once it gets that shared memory segment, I hope does the pointer work? Okay. Okay. So here is the shared memory segment on the right, which gets mapped into the address space of Postmaster. And the next thing that happens after it has got that shared memory mapped, its address space reserved, it goes and chunks that shared memory into the different structures, like what we are seeing here. I have just listed the buffer manager related structures, but there are many, many more. Now, once it has chunked it, it reserves the first chunk for what is called a shared memory index, which is basically a hash table of where each of those structures is within the shared memory. And then once these chunks are created, each of these chunks gets an address, memory address to it, and that memory address is stored in the global variables in Postmaster. So at this stage, the Postmaster is ready with the shared memory segment created. Now it goes ahead and creates a child process, when either it is a worker backend or it's a backend which connects to a client. And things start getting more interesting here. In Linux, it basically is, the child is exact image of the Postmaster. And by image, everything that is in the Postmaster memory, well, I think except for heap and stack, gets replicated into the child process. So whatever global variables were set in Postmaster, they get the same values in the child process, in the worker backends. So you will see that, now that those global variables are set, they have the values, or they have the addresses of the shared structures that the Postmaster has set up initially. Interestingly, the shared memory also gets mapped at the same address space in the child processes as well. So the addresses that were held into the global variables still point to the structures that were created by Postmaster, even if it's now a new process. So now you would ask, what's the purpose of that shared memory shmem index, right? shmem index that was created, which is stored at the beginning of the shared memory. There is a separate set of operating systems, I would say, like Windows, which do not do this, which do not fork a process in this manner. They just basically what we call as the fork and exec. So they fork the process, but then it is all its memory is wiped out. And so along with that, all the shared mapping and everything goes away. We do some magic and tell that child process that here is your shared memory segment, here is your shared memory ID, and you should map the corresponding shared memory at this address space. And so on Windows, we have some code which tries to map that shared memory ID at the given address space, so that the pointers that are stored in the shared shmem index are still valid. So the child process then goes, looks up each of these data structures in the shmem index, and then sets its pointers. That's how a Windows backend gets created. Now, so I mean, I think I have given a very high-level overview of how the shared memory is set up, but if you go into the details, it's much more complicated than this. Just hold on to this while we also talk about, If you want to find out what all chunks of shared memory are available, then there is a view called PGConf allocation, on which you can query and find out what are the structures, how much of each is of size, what's the offset of that structure within the shared memory segment, and so on. And so you will see multiple buffer manager related structures there. So now let's talk about the shared buffers. Hold on to that information and let's talk about shared buffers. What are the structures that are involved in when we call a shared buffer pool? So the very first structure is buffer descriptor. If there are n buffers, there are n buffer descriptors which tell you the state of each of those buffers along with buffer ID. Which is basically, as it says, it's an identifier of that buffer, and it is 0 based and it's sequential, in that array, as if we actually store the index of that buffer descriptor in that structure itself and call it as a buffer ID. The second structure is buffer blocks, which is actually the memory which holds the pages. And there is another one, and then there is the third one, which is conditional variables. All these three are arrays, and there is one more which I think I have forgotten about checkpointer buffer IDs. All of these are arrays. They are contiguous chunks of memory. And then there is fifth structure, which is a buffer lookup table, which is nothing but a hash table to which we give the page tag. It does some mathematical calculation, looks up the index in the hash table, traverses the linked list, and matching the tag and finds the buffer ID. Usually this memory of the hash table, the indexed table, and also these blocks, the buffer entries, they are again contiguous chunks of memory. So now let's put this together, and what we want the buffer manager to have is the shared buffer structures contiguously in the memory, and many of them stacked one after the other, put one after the other. So now if we want to increase the number of shared buffers from 50 to 100, 100 to 200, or 1000 to 2000, what we have to do is somehow elongate these arrays. Why we can't just reallocate that memory somewhere else? Because as I said in the very first slide, the pointer to these all arrays has to be stable. It has to be same across all the backends so that those backends can find those buffers at the given location. So we cannot just take the array, reallocate somewhere else, copy the content. Reallocate doesn't work here. It's not an option. What we need is these arrays also need to be elastic. They need to grow and shrink as the buffer pool increases and decreases. So that's the first problem. How do we make these structures elastic? How do we make these structures resizable? And then the second problem, which is actually the part about open heart surgery, is all the backends. There is hardly any backend which does not touch shared buffers in its lifetime. There are some backends which are special, which do not touch shared memory at all, but most of them do. Like right at the time of authentication, every backend touches your shared buffers. So While all these backends are running, they are trying to access shared buffers, allocate new, modify something, deallocate something, add a new page into the buffer manager. While all this is happening, we want to elongate these arrays or shrink them. If we say that no, everybody has to stop what they want to do, then we will resize it. That's a simpler problem to have, but then you would rather restart the server, So that's the second problem. So the resizable buffer pool is actually two problems. One, how do we make shared memory resizable? And second, how do we make sure that all these processes that are accessing shared buffer, doing something with them, continue to do that without getting disturbed, without getting hazards. It should not happen that a backend which was holding to page 2 now suddenly sees page 3 there, or which was holding to page 2 does not anymore have that page 2 at that location. All those hazards we need to make sure they don't exist, and yet we want this resizing to happen quickly and without disturbing the load that is already running. So how do we solve the first problem? We talked about 3 different techniques, and I'm giving a, I would say, the backstage view of how development happens in PostgreSQL. So I'm instead of telling you what's the current status, what we are doing, I would walk you through all the possible solutions that we discussed. Although I will start with the approach that we are taking right now as the first one. So what we are doing is we still map shared memory. We still we still request OS to give us address space which is large enough to hold maximum shared buffers that a user wants to configure. And then out of that, when we are chunking the shared memory, what we do is we create the chunks, but if a structure needs to be resizable, we reserve some address space after that structure. So we allocate memory that the first request has, and then still shared address space where there is no memory, it's a hole. So for example, if ultimately you want to grow the buffer pool to, let's say, 1 gigabyte, but you are starting with just 128 MB, which is default, the buffer blocks will have 128 MB of memory allocated, and the rest of 1 GB minus 128 MB memory as reserved address space, where there is no backing memory. It's just a hole. Okay? That's the first solution. And then as we grow, we basically tell OS that, okay, now I'm going to use this reserved space, please allocate memory there. When we want to shrink, we tell that, okay, this memory I was using is no more useful, please take it away. But the reserved address space still remains there. That's how we achieve the resizable or elastic structures. But before that, I mean, before we arrived to this solution, and this was a development that happened, let's say, in last 2-3 months, we were taking a different approach where each of these resizable structures had separate mmapped memory. We were asking the operating system to give, if there are 5 buffer manager structures, I was asking 5 different segments to be mapped to the postmaster address space for 5 different structures, each structure getting one segment. And then within that segment, we could resize the buffer, I mean resize the memory using mmap, memory map, tweaking its protection and so on. The problem with this is, we saw fork. The number of segments we have, number of segments mapped to the address space we have, that increases the amount of time fork takes. And worse, in Windows, where we have to attempt to get the address space of our choice, we have to do multiple calls to the system for every segment, which again bloats the amount of time that we require to get the segments. We talked about this. Then there was another approach that was considered, because mremap, it seems, does not work with huge tables, and many of the customers use huge tables to reduce the amount of mapping tables that OSs maintain. So there we use slightly different approach, where we used anonymous files as a way to manage memory, and then mmap to manage the reserved space. But that again added another layer of file descriptors, which required, when forking, they were required to be copied into the child process, increasing the amount of time it takes to fork. And the solution that we are right now using is MadWise, using MadWise, which is, I think, there is a recent development in MadWise where, well, I should call it M-Advise, not MadWise, but it's really mad. I mean, that call is really mad. So what it does is, if you tell it that this amount of the memory from address space X up to length L from that address space, I don't need anymore. You say madv remove, then the OS will take away those pages immediately. Similarly, if you tell it to write populate, it will put the pages into that address space and allocate the memory. So without going through the file descriptor and maintaining those, we still get the similar functionality. And this is the approach that we are taking now. Okay, so what it takes, now let's get slowly into the actual operation, how resizing happens. So when we want to shrink, from, let's say, 1 GB to 128 MB, we first tell all the processes. I think we'll come to the synchronization part, but let's talk about the protocol first. So first we evict all the buffers from the extra portion that we want to shrink. We flush dirty buffers. There can be pinned buffers there, which creates problem, and I think right now we have to just abort the operation if we find a pinned buffer. Then we have to empty the extra elements in the buffer descriptor array, in the checkpointer IDs array, in the conditional variable ID array, and then go remove the entries from buffer lookup table. At this point, nobody should be accessing the buffers that we are shrinking. Then we can go ahead, we publish the new size. Okay, here is the new size. Then then just shrink those structures first, and then shrink the memory. Tell OS to take that memory away. We don't do anything with the buffer lookup table right now, because the way buffer lookup tables in PostgreSQL are arranged, they have a directory which is fixed size, and then the entries which are in a separate allocation. And those entries are not necessarily contiguous. I mean, they are in contiguous memory, but not necessarily contiguous. So the buffers we have evicted need not be contiguous. We can't just shrink those pages. We can't just say, take these pages away. There might be some entry there which is still valid. When we are expanding is relatively easy because everybody is using that gray, everybody is using the gray area which remains untouched, the gray area in the first image, it remains untouched. All we do is we tell OS to add some more memory, initialize that memory, and tell everybody that, okay, here is new size that you can use. Although it's not as easy as it seems. I mean, there is some synchronization still required. I mean, imagine the case where one backend added a buffer in the new memory, but the other backend is yet to know that this new size is available. So we told one backend, here is your new size. But before we go and tell other backend, here is your new size, that first backend could have allocated a buffer in the new memory, and this second backend had tried to exactly get the same page, and it will see that it's in a area which according to it is not there. So it will just start throwing segmentation faults and so on, or maybe it will just error out. So we have to make sure that those things do not happen. Those things happen in a synchronous way. So how do we synchronize? How do we do this surgery, this open heart surgery, while all the other backends are still running? They are still accessing buffer manager, buffers. For that, we have a mechanism called proc signal barrier. It's a way to tell everybody that, okay, here is the new state. Go and update your new state. Go and update your local state. Then everybody says, okay, I have acknowledged this state, I have acknowledged this state. When every backend has acknowledged that state, you can go on to the next stage of doing something. Interestingly, now this is the beauty of how PostgreSQL development happens. This facility of proc signal barrier wasn't there until online checksums was being worked upon, which was something that my colleague started, Daniel Gustafsson, he started 5 years back. And at that time, he didn't have this facility of getting a consensus across the cluster. So, and he did his work in a very different manner. Andres came and said, no, we need consensus. We can introduce consensus here. He put the proc signal barrier in there. That patch is still being discussed on Hackers, the online checksum patch. But now it helps the buffer resizing work as well, because we are now able to use the mechanism which is already there to have a consensus. Anyway, so what happens is there is a coordinator, basically a backend which controls or coordinates this operation. It starts and says, if it's shrinking, then it says, I'm going to shrink the buffer pool to this new size. All the other backends then restrict their activity to this new size, which means that they allocate new buffers in the new size. The old buffers that were being still used, they continue to use it, but the new buffers always get allocated in the new area. Once everybody acknowledges this new area, the coordinator knows that there are no more new allocations happening in the area that is being shrunk. It can go ahead then and start evicting those extra buffers. Hopefully by this time, all the processes have allocated their new buffers in the new area and unpinned the buffers that they were already using. If that happens, we evict all the buffers and we go ahead to the next step. If the coordinator finds a pinned buffer, it just says, no, we can't do it, we can't shrink it right now, try again. Once that phase finishes, it goes and it has evicted all the buffers, nobody is accessing that area. It goes and says, this is that new area is now permanent. You are no longer going to need the rest of the area. Once all of the backends acknowledge and accept this, it goes and then resizes the shared memory, gives memory back to the OS. If we are expanding at this stage, the coordinator tells everybody that, okay, we are going to expand to this new area, expect new buffers in that area. So everybody prepares for those new buffers. It goes, initializes the expanded memory, adds those new buffers, and then tells everybody that the new buffers are available. The backend start using it. And because of the earlier proc signal barrier, they are aware that, okay, my view says that the buffers are up to this limit, but I also know that we are expanding to this new size. So even if they see a buffer in the new size, they have already prepared for that, and they do not panic seeing that area. Once all of this happens, everybody accepts the new area, new size, you resume the normal operation. Easier said than done, but that's the simplest way of explaining it. There could be failures, as I said, pinning or those system calls may return failures, in which case we are not sure what to do. Like, I think that right now the brute force is we just abort the operation, go back to the old size. We cannot panic, we cannot stop the server, because we want this to be done while the server is running, but we just roll back the operation and go back to the earlier size that we were working with. Still, there can be some irrecoverable failure where restart will be needed, but we try to minimize them. Yeah, but still there could be possibilities when a restart will be needed. But anyway, if if this feature wouldn't have been there, you would have restarted anyway. So I think that's a safer fallback. Now this is how it looks from user's perspective. Okay, we talked about how it is done in backend, but this is how it looks from user's perspective. Show shared buffers, probably you are familiar with. They give the amount of memory, that amount of size of the memory in the buffer blocks. If we want to change the shared buffers, we say alter system set shared buffers, then do a pg reload conf. Up to this, you were already doing these steps. The only thing that was not happening is this pg reload conf was not reloading the new buffer size. And it will not still. PG reload conf is not going to just resize the buffers behind the scene. But it will start showing, when you do show shared buffers after this, it will show you the size that it intends to be, like this pending size. And once you see it there, if you execute pg resize shared buffers function, then it will execute what that coordinator was, I said, would execute those steps, and if it succeeds, it will return a true status. And after that, if you do show shared buffers, you will see the new size. If you go into and look at the process memory, you will see the memory also adjusted accordingly. That was shrinking. Similarly, expansion, we have the same steps. Nothing changes from user's point of view. Okay, a slight note, this is all being developed for Linux. We still don't have, this solution may not work in Windows, at least in first version whenever it lands. That's because the APIs, the requests that we are making to operating system, we don't know, or some of those requests are not available on Windows. Or we have to change how we request Windows to resize the memory and so on. But I hope eventually we will also have that support in Windows once the Linux support matures a bit. Well, those who are aware of multi-threading efforts happening in community, people will ask what happens when there is multi-threading, because then shared memory is just a global array, right? You don't need shared memory for that. But still, the memory mapping and this elastic shared structures we still require, so that the processes don't have to synchronize on the location of these structures again. So I think some of these things will continue to be there. The process synchronization may be simplified a bit, but I don't see that the need for this feature will go away.